Hello, this is Seth Holder, and this is my Lab 3 on the black hole. For a quick introduction on this lab, it's composed of two parts. In part 1, we analyze the motion of a star to determine the mass of a black hole. Uh, we do this by using a computer simulation via GlowScript to find the mass of the black hole by analyzing a star's orbit around it. In part 2, we calculate the initial velocity of a spaceship to get it to form a figure-8 pattern around a planet and its orbiting moon. The purpose of this is finding an initial velocity of a spaceship must have to leave the surface of a moon and fly around the planet in a figure-8 orbit, and these demonstrate the effects of Newton's second law and its relationship with momentum. In our system, or in our equations, the system is the black hole and the surroundings are the star, or the spaceship. These are a few fundamental principles and models we use during our calculations. We use Newton's law of universal gravitation because we're in space with two heavy objects. We use Newton's second law for F-net. We use the velocity and position update formulas, and we use parallel and perpendicular forces. This is the initial conditions in our GlowScript code, showing you what our G is equal to, what the mass of the star is equal to, our delta T, and just everything we did before calculation. This is our calculations that we did. As you can see, we found everything we needed to find F-net, V initial, V final, P initial, P final, delta V, delta P, everything for F-net, and then the perpendicular and parallel forces. And then at the bottom, you can see that we use those to find the mass of the black hole using the gravity equation. This is the graph that we got for the orbit after we used that calculation. As you can see, you have the force and position arrows, and we also can see how the black hole, it's not a perfect mass, but it's around 9.7 times 10 to the 33 kilograms, which is what we got our mass of the black hole to be. This is the second part of the lab with our initial conditions, the gravity, the mass of the planet, mass of the moon, mass of the ship, delta T, and just the initial conditions needed. As you could see at the bottom, ship speed X and Y, those are the initial conditions that I used for the ship to try to orbit the moon. This is the next part of the calculations. This is finding the forces that are acting on each object. The forces acting on the moon, the ship, the planet, all of that. Because the planet's so big, it doesn't really move, but the moon and spaceship do, and these calculations just get that to work as we find the velocity and position, and we use the velocity and position update formulas, as well as the forces to really get the correct positioning. This is the results I got. It's nearly impossible to find an initial velocity that results in a symmetrical figure-8 orbit, and so this is just it somewhat being affected by both the moon and the planet. We then have some possible errors, such as the approximations we used. Since this is a simulation, it will not always represent reality, and we're assuming that there's no other outside forces acting on the system. There's also the accuracy. We use trial and error to find velocities, and to get the spaceship to make a figure-8, again, the measurements would have to be very precise and very difficult to find. Discussion question. We started off with how is the net force and its parallel and perpendicular components different from the rate of change of momentum? And mathematically, they're the same. However, the momentum change is much easier to calculate. We need to know every external factor acting on the system for the net force and its components. However, for the rate of change of momentum, we only need the change in velocity of the system, which is why we use dp dt. This imaginary system has a black hole, a star, a planet, and a moon. If we wanted to predict the motion of the entire system, what would we need to include in our computational model? Like just thinking about all the interactions in the system. We would need to consider all the parts of the surroundings that are acting on the system in any way, and vice versa. And there would be dominant forces between the star, moon, and black hole. So we just have to think about every single thing affecting the system while it's moving.